Welcome back. In our previous video, we tackled an initial value problem, or IVP, where the starting condition was given at t equals 0. But what if the initial condition is specified at a different time, like t equals a? Don't worry, it's simpler than you might think. Today, we'll break it down step by step. Each video in this series builds on concepts from the previous ones. If you're just joining us, we recommend checking out the earlier lessons and practicing along the way. Remember, practice makes perfect, especially in mathematics. In this video, we'll explore what to do when the initial condition is given at t equals a instead of t equals 0. The key adjustment is simple. We integrate from a to t, rather than from 0 to t. This ensures that our solution accurately reflects the initial condition at t equals a. Let's dive in and see how this works. When the initial condition starts at t equals a, the only change is in the integral's lower bound. Everything else remains the same, including our initial guess. By integrating from a to t, we ensure that our solution aligns perfectly with the initial condition at to t, delivering accurate results for initial value problems. Let's dive into an example and see how to solve an initial value problem with a non-zero initial time using the Parker and Sochacki method. Consider the differential equation. With the initial condition. This example will help us see how to handle cases where the initial condition is specified at t equals 1. Let's walk through the solution step by step. To solve this initial value problem iteratively, we use the following iterative formula. Here, our initial guess is. This iterative approach allows us to refine our solution step by step, ensuring it satisfies the initial condition. Let's see how this works in practice. In the first iteration, we substitute our initial guess into the iterative formula. For the second iteration, we use the result from the first iteration in the iterative formula. In the third iteration, we use the result from the second iteration. The exact solution to the differential equation. With the initial condition at t equals 1 is. Let's compare this exact solution with the results from our iterative method. To compare the exact solution with our iterative approach, we need to find the Taylor series expansion of the exact solution. But you might be wondering, what exactly is a Taylor series expansion? While fully exploring the Taylor series is beyond our current scope, let's review the basic idea. A Taylor series represents a function as an infinite sum of terms, where each term is based on the function's derivatives at a specific point. If that point is 0, it's a Maclaurin series. In our case, since we're expanding around t equals 1, We use a Taylor series centered at t equals 1. This allows us to approximate the function near this point using polynomials, making it easier to analyze the function's behavior and compare it with our iterative solution. In the previous slides, we calculated 3 approximate solutions. When we compare these approximations to the Taylor series expansion of the exact solution, a clear pattern emerges. The first approximation matches the first 2 terms of the Taylor series. The second approximation aligns with the first 3 terms. The third approximation corresponds to the first 4 terms. This progression shows that with each iteration, we're including an additional term from the Taylor series, improving our solution's accuracy. This demonstrates how the iterative method approaches the exact solution as we refine our estimates. In this slide, let's quickly compare the Taylor series and the Maclaurin series. A Taylor series approximates functions using infinite polynomials, centered at a given point, A. The Maclaurin series is a special case of the Taylor series, where the center is 0. In our example, we expand around the point t equals 1, using a Taylor series centered at 1. If you're enjoying this video so far, don't forget to like it, share it with others, and subscribe to the channel for more videos like this. If you have any questions or thoughts, drop them in the comments below. We'd love to hear from you. Now, let's introduce a more efficient approach, the change of variables method. By redefining the time variable, we can transform the problem into one with an initial condition at 0, simplifying the solution process. This method allows us to handle problems that would otherwise be more complicated, making them easier to solve by shifting the initial condition to a more convenient point. Let's see how this method works in practice. Now, let's revisit our example. The differential equation. With the initial condition, we'll apply the change of variables method to transform this problem into one with an initial condition at 0, making it easier to solve. Let's walk through the process step by step. Let's define tau equals t minus 1. This change of variables shifts the initial value from t equals 1 to tau equals 0, transforming the problem into an initial condition at 0. Let's see how this works in the next step. In the next step, we'll take the derivative of tau with respect to t. To do this, we need to use the chain rule. The derivative of tau with respect to t is 1. This shows us how tau changes with respect to t. This step is crucial because it helps us properly adjust the equation when we switch from t to tau. Let's proceed to the next step. Now, we have successfully transformed our initial value problem, and the initial condition is now at 0, which simplifies the problem. With the initial condition at a convenient value, 0, we can solve the problem just like we've discussed in previous videos, using integrals with lower bounds at 0. This allows us to apply the methods we've already covered and efficiently solve the differential equation. In our previous video, we thoroughly explored this iteration. To avoid redundancy, we'll proceed with the results obtained earlier. Now, let's substitute back into the original variable. Recall. After performing the substitution, we find that our approximate solutions align perfectly with the Taylor series expansion of the exact solution. Thank you for staying with us throughout this video. In our next video, we'll introduce an innovative approach featuring a new algorithm developed by Hamid Semiyari designed to approximate solutions for boundary value problems. Unlike traditional methods, this technique is computationally efficient and capable of handling complex problems with ease. Get ready to explore a powerful tool that makes solving boundary value problems more accessible and exciting.